In the last video, we talked about system calls, the mechanism your code uses to interact with hardware with the help of kernel. But we didn't answer a more fundamental question: why does this boundary exist at all? Why can't your code just run whatever instruction it wants? The answer comes down to something the CPU enforces at hardware level. CPU can operate in two different modes. User mode is where all your application code runs. It is a restricted environment. Your code can do arithmetic operation, read and write its own memory, call functions, but it cannot execute privileged instructions and it cannot touch hardware directly. Kernel mode is where the OS kernel runs. Code here has full hardware access. It can execute any instruction the CPU supports, modify memory map, control register, manage devices. The critical thing to understand is this is not a software setting but a hardware mode which is tracked by the CPU itself. The x86 architecture implements this through a concept called protection rings. There are 4 privilege levels numbered 0 to 3. Ring 0 is the most privileged. The kernel runs here. Ring 3 is the least privileged, and this is where all user space applications run. Ring 1 and 2 exist in the architecture, but modern operating systems don't use them. They were originally intended for device driver, but in practice both Linux and Windows use only ring 0 and ring 3. The lower the ring number, the more privilege it is. Ring 0 can do everything ring 3 can and more. So, what are these privileged instructions? The CPU has a class of instructions that can only execute in ring 0. If ring 3 code attempts any of them, the CPU raises a general protection fault and the process is killed. Some of the privileged instructions are hold. This holds the CPU entirely. Only the kernel should be able to do that. CLI and STI, clear and set hardware interrupt. If a user process could do this, it could block the kernel from regaining access of the CPU. In and out, direct I/O port access. This is how your code talks to hardware devices at the lowest level. Move CR3 loads a new value into the page table base register, which controls the entire memory map. Only the kernel should be able to manage memory mappings. The pattern is the same across all of them. These are operations that affect shared system resources. Letting unprivileged code run them would break the isolation between processes and between user code and the kernel. How does the CPU know which mode it is in? Through a value called current privilege level or CPL. The CPL is stored in bits 0 and 1 of the CS register, the code segment register. CPL equals 0 means the CPU is in kernel mode. CPL equals 3 means user mode. It is checked on every single instruction fetch. Every time the CPU decodes an instruction, it checks whether the current privilege level permits that instruction. Now, how does code actually move between these two modes? Going from user mode to kernel mode, it's called elevation and only happen through controlled entry points. A system call, a hardware interrupt, or a CPU exception. The key point is that these entry points are all defined by the kernel and not by the caller. User code cannot choose what runs at ring 0. It can only trigger a transition and the kernel decides what happens next. Going the other direction, kernel back to user, the kernel controls this. It uses instruction like sysret or iret, which restores the save user space register state and drops the CPL back to 3, and execution resumes in user space exactly where it left off. This asymmetry is essential for security and isolation. User code can request elevation, but it cannot dictate what elevation does. The mode boundary does not just control which instructions can run, it extends into memory access as well. Every entry in the page table has a user or supervisor bit. Pages marked supervisor are only accessible when the CPU is in ring 0. When the ring 3 code tries to read a supervisor page, a kernel memory page, the CPU raises a protection fault, which is a specific type of page fault caused by a privilege violation. The kernel's fault handler sees the violation and kills the process. This is why a user space code cannot read kernel memory. Let's recap everything we learned so far. The CPU runs in one of the two modes, user mode at ring 3, kernel mode at ring 0. This is a hardware state and not a software setting. Privileged instruction can only execute in ring 0. Attempt them to run in ring 3 and CPU raises a general protection fault. The process is killed immediately. The current mode is tracked through the current privilege level stored in the code segment register. It is checked on every single instruction fetch. Moving from user to kernel mode can only happen through a system call, a hardware interrupt, or an exception, and the entry points are always defined by the kernel, never the caller. Moving back from kernel to user mode is explicit. The kernel drops privilege using sysret or iret and restores the saved user space state. And finally, memory protection extends this boundary into the page table. Supervisor pages are inaccessible from ring 3. That's it for today's video. I hope you now understand all about user mode versus kernel mode. If yes, then please do like this video and comment down if you have any questions or if you want me to cover any other topic. Subscribe for more such content. See you in the next one.